the identity-based encryption system was to implement a public key infrastructure for an email system. So you'd have some key granting authority that would kind of play the part of the public key infrastructure, I guess. And there were basically 4 parts to this. One was a setup algorithm, and this key generating authority would run this algorithm and generate some public parameters that everybody would know. It would also generate some private parameters like a master key. And there was an extract algorithm that if you had the master key for any string, you could create a private key corresponding to that string. And also, but if you had the public parameters, you could generate a public key for any string. So the encryption algorithm would take any string as its input, would be able to create a public key towards that, and then encrypt it with that public key. And if you had the private key for that public string, you'd be able to run a decryption algorithm to decrypt messages. This is fairly nice for an email system because if I have someone's email address, well, I can get the public key because I have their email address, so I can create the public key for that. And the key generating authority won't give them the private key unless if they're the person corresponding to that email address. So I kind of have a public key infrastructure, and I don't really have to talk to the key generating authority other than once for everybody. There was some work in 2003 on hidden credentials, which was kind of a starting point for this work. And the credentials are generated by some certificate authority, and it uses this identity-based encryption. So this is a quick example. Suppose the certificate authority wants to issue Alice a student credential. Alice could be some form of pseudonym, or it could be Alice's email address or something like that. Now, he could use the identity-based encryption with the ID of Alice concatenated with student. And if he agrees that Alice is a student, then he can give her the private key corresponding to this ID. And if she's not a student, he wouldn't give her this. So this credential authority kind of plays the part now of verifying whether or not Alice should gain access. Just as a quick example, suppose Bob wants to give Alice a message M, where the message M should only be read by someone that's a student. So Alice asks Bob, "I'd like message M," and Bob would then compute the public key for the ID Alice concatenated with student. He would send Alice this value. Now, if Alice has a student credential, she'll be able to go to the certificate authority and say, "I would like, the private key," or she probably already has that if she has that attribute. So then she can decrypt the message. Now, note that Bob does not learn whether or not Alice is a student, but Alice only gets the message if she is a student. This doesn't, even in this simple case, this doesn't solve what we were proposed earlier, because note that Alice does learn Bob's policy if she gains access. Before we get into the protocols, a quick note on how we're going to define the policy. And we're going to define this simply by some Boolean function p over some values x1 through xn, where the x values are binary values. And the xi corresponds to the absence or presence of an attribute I. Now, if Alice's set of credentials will satisfy the policy if we let these x values, xi will be 1 if there's a credential that corresponds to attribute I. So if the p function of these x values is 1, then Alice should gain message. It satisfies the policy, otherwise she doesn't. As a quick example here, suppose Alice is a senior citizen and has a low income. Furthermore, suppose the policy is you need a disability or be a senior citizen and have a low income. Well, Alice satisfies this policy because she is a senior citizen, which would correspond to x2 here, which is 1, and she has a low income, which corresponds to x3. Therefore, the policy function values are true. So there are 2 parts to being able to do our desired goal. The first is that we kind of need the credentials and the attributes to be hidden in some regard. Alice has a certain set of credentials, Bob has a certain set of attributes in his policy. We kind of need it so that Alice and Bob are speaking some language that the knowledge of which attributes Alice has is both verified by a certificate authority, but also is done in a way that neither Alice or Bob know which credentials or attributes the other side is using. And the way we're going to choose to represent this, the goal of this phase is that Bob will have 2 random values that he's generated, RI0 and RI1, for each attribute. And Alice will know one of these values, and only one of these values. She won't know which value she has, but she'll have exactly one of them. And furthermore, if her value ki is ri1, that means that she has a credential for the attribute. If ki is ri0, that means she doesn't have, or she didn't use a credential for that attribute. Now, note that Alice doesn't need to necessarily know which value she has. The RIs are chosen from a fairly large domain, so she can't just guess a bunch of RI values to guess the other one. Once you have things in this format, the goal is to take this and then basically evaluate the policy function P. The hiding phase is actually, of the two phases, is the more difficult of the two phases. Suppose Alice has a certain set of credentials C1 through CM, and that Bob has these n pairs of random values that he's generated, Ri0 and Ri1, each corresponding to some particular attribute. And the goal is, though, Alice will get one element from each of these pairs, and it will be Ri1 if she has some credential C sub j where the attribute for C sub j is attribute I. The first step is Bob's going to generate n pairs of another, for each attribute he'll generate another pair of random values, ki0 and ki1. And the goal will be to kind of slowly work towards the desired output by having the value split in some other fashion. So to begin with, Bob will send Alice, he'll encrypt for each attribute, he'll encrypt ki0 with Alice concatenated with the ith attribute. Now Alice, if she has attribute I, she'll be able to decrypt this and get ki0. But suppose she doesn't have attribute I. She doesn't know what attribute I is, so she'll basically try all of her credentials. She'll try the private keys for all of her credentials. When there's not a match, she's decrypting something with the wrong key. When you decrypt something with the wrong key, you get something that looks random, that looks like garbage. But this is no different looking than ki0 because ki0 was generated from the beginning to look like random looking garbage. So she doesn't know, when she decrypts all of this, she doesn't know if she has the particular attribute or not. But she can create, for each attribute, a set of size m, which possibly would contain the value ki0. It will contain ki0 if she has it. It won't contain ki0 with all but a negligible probability if she does not have the credential. Now this is where the set intersection protocol comes into play, because Alice and Bob engage in the set intersection protocol with ki0 being Bob's input and bi being Alice's input. Now, at the end of the protocol, though, Bob would like to reveal out to Alice ki1 if ki0 is in bi, and otherwise reveal some random looking value. This doesn't reveal anything to Alice either, because ki1, again, is a random looking value, and so it's indistinguishable from a random looking value from something not being in the set. At this point, though, Alice will have the credential if her value that she got in this previous step will match ki1. So now we're basically in equality. If they match, Alice has the attribute. If they don't match, she doesn't have the attribute. Note that Alice does not know if she has the attribute or not. That's been questioned. And Bob doesn't know if she has the attribute. And there are, using a scrambled circuit evaluation, it's a fairly simple circuit to implement where Bob's input's ki1, Alice's input is the value. If they're equal, Alice will learn ri1, and if they're not equal, she'll learn ri0. So just kind of an overview here. We started out with the information completely split between Alice and Bob, and we've kind of did 3 steps here to transform it into this format where Alice has one value if she has the credential, and the other value if she doesn't have the credential. Are there any questions on this phase? It's kind of the...
Yeah. Sorry. So these are just Bob send these to Alice.
No, he creates them. He creates them on his own system.
So I guess I'm a little confused when you say she gets R1.
She learns the in scrambled circuit evaluation. You get to choose 2 encodings for each wire.
And this circuit evaluator is sitting at her end, or
Bob generates some